There's this hidden chemical force all around us, and even inside of us, that's constantly working to keep everything in perfect balance. So today, we're going to pull back the curtain on these unseen guardians of pH, chemical buffers.
I mean, seriously, think about it for a second. You can down a glass of something pretty acidic, like orange juice, and your body's internal chemistry just handles it. It barely even flinches. How is that even possible? Well, the answer lies with those chemical guardians we just mentioned.
See, here's the deal. pH balance is incredibly delicate. For a lot of solutions, just leaving them out in the open can make them more acidic because they're absorbing CO2 from the air. And get this, even the glass bottle they're stored in can be a problem since tiny impurities can leak out and mess with the pH. So without some kind of defense mechanism, stability would be almost impossible.
So, what's the solution to this constant chemical threat? All right, let's meet our chemical guardians. Okay, so this is the classic textbook definition. But let's break it down. Think of a buffer as a chemical bodyguard. Its entire job is to just stand there in a solution and fight off any small amounts of acids or bases, alkalis, that try to rock the boat and change the pH. They're the reason that stability we talked about is even possible.
Now, these guardians don't work alone. They come in specialized teams. You've got two main types. First, there are acidic buffers. That's a mix of a weak acid and its salt. Then you have basic buffers, which combine a weak base and its salt. Each team is custom-built to defend a different kind of pH environment.
So, we know who they are. But the real question is, how in the world do they pull off this incredible balancing act? Let's dive into the mechanics. This amazing ability to resist change is called buffer action. And probably the best way to picture it is like a chemical shock absorber, or maybe even a sponge. When some disruptive acid or base comes along, the buffer just soaks it up, neutralizes the impact, and stops the pH from flying out of control.
The strategy here is just brilliant. It's a two-part defense. Remember that team, the weak acid and its salt? Well, one of those components is on standby, ready to neutralize any acid that shows up. And the other component? It's ready to take on any incoming base. With both defenses ready to go, the buffer can hold the line against anything.
And this isn't just random chance or chemical guesswork. Scientists can actually design these buffers for very specific jobs, and they do it using a really powerful formula.
Okay, here it is, the Henderson-Hasselbalch equation. I know, it looks a little intimidating, but trust me, it's really just a recipe. It's the exact tool that lets a chemist figure out the pH of a buffer solution, as long as they know the ingredients, the amount of acid and the amount of its salt.
And this equation doesn't just appear out of thin air. It's derived from some pretty fundamental chemistry. You start with the basic expression for an acid. Then, with a few clever steps of algebra and a conversion to the pH scale, you can rearrange everything to create this incredibly useful tool for calculating a buffer's exact pH.
All right, theory's great, but let's put this recipe to the test. Let's say we've got a buffer solution. We know the pKa value, which is basically just a number that tells us how strong the acid is. So how do we find its pH?
Here are our ingredients all laid out nice and clearly. We have the pKa for our acetic acid, we have the concentration of our salt, the sodium acetate, and the concentration of our acid. Now all we have to do is plug these values into our formula.
So we take our pK, which is 4.57, and we add the logarithm of the salt's concentration, 0.1, divided by the acid concentration, 0.03. You run the numbers, and what do you get? A final pH of 5.09. It's that predictable. Pretty cool, right?
But this is so much more than just a formula in a textbook. Let's explore where these chemical guardians are silently at work every single day all around us and, yeah, inside of us.
I mean, the applications are literally everywhere. In our own bodies, buffer systems work around the clock to keep our blood pH locked in at a stable 7.4. If that number changed even a little, it would be catastrophic. And in medicine, buffers are absolutely essential for making sure drugs are stable, safe, and effective. They're used in injections, in eye drops to stop them from stinging, and even in creams and ointments to make sure the product doesn't go bad.
And here's a perfect example of just how critical this is. For anything that's going to be injected into the body, the ideal pH is 7.4 to perfectly match the pH of our blood. And that's not just a nice to have, it is a vital safety measure to prevent serious pain and damage to our tissues.
All of this just goes to show how essential these buffers are, from our own bloodstream to the medicines we rely on every day. So it makes you wonder, right? What would actually happen if these unseen guardians failed?
It's a quiet but constant chemical battle being fought all around us, and thankfully, it's one we're winning.